So this is part 189. It's line 18a5. We're on to another section. Thermodynamic equilibrium reversible process Infinitesimals 5G Wow Seti. So there's the alien radial signal. Again, this is more data. Quotes from Wiki: in thermodynamics, a reversible process or reversible cycle is a process that can be reversed by means of infinitesimal changes in some property of the system without loss of dissipation or energy. Due to these infinitesimal changes, the system is in thermodynamic equilibrium throughout the entire process. Since it would take an infinite amount of time for the reversible process to finish, perfectly reversible processes are impossible. However, if the system undergoing the changes responds much faster than the applied change, the deviation from a reversibility may be negligible. In a reversible cycle, the system and its surroundings will be exactly the same after each cycle. An alternative definition of a reversible process is a process that after it has taken place can be reversed and cause no change in either the system or its surroundings. In thermodynamic terms, a process taking place would refer to its transition from its initial state to its final state. Another quote from Wiki: infinitesimals have been used to express the idea of objects so small that there is no way to see them or to measure them. The word infinitesimal comes from a 17th century modern Latin coinage infinitus, which originally referred to as the infinite item in a series. In common speech, an infinitesimal object is an object which is smaller than any feasible measurement but not zero in size, or so small that it cannot be distinguished from zero by any available means. Hence, when used as an adjective, infinitesimal in the vernacular means extremely small. Archimedes used what eventually became known as the method of indivisibles in his work The Method of Mechanical Theorems to find areas of regions and volumes of solids. In his formal published treatise, Archimedes followed the same problem using the method of exhaustion. The 15th century saw the work of Nicholas of Cusa further developed in the 17th century by Johannes Kepler. Again, Johannes Kepler has come up in other videos with his satellite and with the Kepler 22b planet. That's a habitable planet, twin of Earth. In particular, calculation of area of a circle by representing the latter as an infinite-sided polygon. Simon Stebbins' work on a decimal representation of all numbers in the 16th century prepared the ground for the real continuum. Bonaventure Cavalli's method of indivisibles led to an extension of the results of the classical authors. The methods of indivisibles related to geometrical figures as being composed of entities in codimension 1. John Wallace's infinitesimals differed from indivisibles in that he would decompose geometrical figures into infinitely thin building blocks of the same dimension as the figure, preparing the ground for general methods of the integral calculus. He exploited an infinitesimal denoted 1/8 in area calculations. The use of infinitesimals in Leibniz relied upon a heuristic principle called the law of continuity. What succeeds for the finite numbers succeeds also for the infinite numbers, and vice versa. The 18th century saw routine use of infinitesimals by mathematicians such as Leonhard Euler and Joseph Lagrange. Augustin Louis Cauchy exploited infinitesimals in defining continuity in an early form of Dirac delta function. As Cantor and Dedekind were developing more abstract versions of Stebbins' continuum, Paul Dubois Redman also wrote a series of papers on infinitesimal enriched continua based on growth rates of functions. Dubois Reynolds' works inspired both Emile Borel and Thoralf Skolem. Borel explicitly linked Dubois-Reymers' work to Cauchy's work on rates of growth of infinitesimals. Skolem developed the first non-standard modules of arithmetic in 1934. A mathematical implementation of both the law of continuity and infinitesimals was achieved by Abraham Robinson in 1961, who developed non-standard analysis based on earlier work by Hedwig Hewitt in 1948 and Jerry's Loss in 1955. The hyperrules implement an infinitesimal enriched continuum, and the transfer principle implement Leibniz's law of continuity. The standard part function implements Fermat's adequately. So I don't know what this has to do with anything. I guess it's just thermodynamic equilibrium, reversible process, and infinitesimals. So those are the three things we have to think about when we look at the next videos, okay?